Please title these notes Limit 6 Notes, Differentiability, and write today's date. By the end of this lesson, you should be able to determine if a function is differentiable, both from a graph and using limits. This is really important because in order to use the rules for differentiation that we've been using, we have to have a function that's something called differentiable. Let's now take a look at differentiability. And differentiability, also known as f of x is differentiable, this is talking about the derivative. A function f of x is differentiable at c if f of x is continuous, just like we were just talking about, and we can find the derivative f prime of c at x equals c. So to be differentiable, we need the following things. One is that the function must be continuous. So we do the test exactly like we did before. Second thing, the derivative, remember that's the slope of the tangent line, must be the same as we approach from the left and the right. And then 3, the derivative cannot be infinity. So on a graph, we can just sort of look and spot these things. F of x is not differentiable at a for each of the following. If there is a discontinuity, so that'd be like this, not differentiable, or here, even though there is a limit, it is not continuous, so f of x is not differentiable. And the reason for this is that if you imagine trying to draw a tangent line at this point, well, there are a bunch of lines that you could make the case for being the tangent line. I mean, here this only touches at one point, this only touches once, and so on and so forth. And while none of those are exactly the tangent line, because the tangent line is sort of that one that just brushes the curve, and there's really only one tangent line per se, this kind of doesn't have any tangent lines. There are a whole bunch of lines that we could draw, none of them is really a true tangent line. Another situation is that we could have a sharp turn. So that's something like this. Actually, that should be moving back on itself. It should just be moving up like that. So right here, this is at A. A sharp turn means that if we were to try to draw a tangent line, well here when we're doing it this way we're sort of drawing tangent lines like this. It's sort of like off the end like this there. But when we come from this side we're drawing tangent lines and it's definitely sloping up while this one's sloping down. And so what's happening is that there isn't a single tangent line that we can draw exactly at A. We can draw a single tangent line over here, we can draw one over here, but not exactly at A. They sort of conflict. The slope of the tangent line coming from one direction is different than the slope of the tangent line coming from the other direction. The final non-differentiable point at A is this one. Here, slope of the tangent line is infinity. And the reason this is a problem really is because this infinitely sloping upward tangent line, it's really caused by a rise over run where the run is 0. And basically what we're doing when we find the slope with a run of 0 is we're dividing by 0. If that run is 0, we have division by 0. Not allowed to have that happen. So these are the three things to look for: discontinuity, a sharp turn, or an infinitely sloping tangent line. So let's do a quick example. At what values of x is f of x not differentiable? Here's our little f of x. And so what we're looking for is we're looking for any discontinuities. So clearly not differentiable. Discontinuities. So that would be x equals -3, x equals 1, and x equals 3 right there. It's also not differentiable at a sharp turn. So that's right here where we have a sharp turn. Anywhere else is fine, so if it's sort of like a maximum or a minimum, that's totally fine. We just can't have any sharp turns. Or vertical tangent lines. And that occurs right here, where x equals -4. Maxima and minima are okay. By definition, their derivative is 0. We can find the derivative. 0 is just a number like any other. We can also determine differentiability if we just have an equation, just like we were doing for continuity. How that works is that for f of x to be differentiable at x equals c, f of x must be continuous and the derivative as we approach from the left must be the same as the derivative as we approach from the right. So our first step, what we're looking for is is f of x continuous? So that means the limit as x approaches c from the left equals the limit as x approaches c from the right equals f of c. Secondly, is the derivative the same as we approach from the left and the right? So what that means is the limit as x approaches c from the left of f prime of x. Notice this prime right there, and that should be equal to the limit as x approaches c from the right of f prime of x. So what we did to check with continuity, we're just doing the same thing with f prime. So let's look at a few examples. F of x equals x squared if x is less than 3, and x squared minus 5 if x is greater than or equal to 3. So first thing we're looking at is f of x continuous. So the limit as x approaches 3 from the left. So on the left-hand side, that's x squared. That's 9. The limit as x approaches 3 from the right. So the right side, that's x squared minus 5. So 3 squared minus 5, or 4. Those limits don't match. So not continuous. Therefore, not differentiable. For our second problem, let's say g of x is x plus 6 if x is less than or equal to -1, and x squared plus 4 if x is greater than -1. Is g of x differentiable? First, let's check, is it continuous? X approaches -1 from the left. The left function is x plus 6, so it's -1 plus 6 equals 5. From the right, that's x squared plus 4, so that's -1 squared plus 4, that also equals 5. So those match. And then g of -1. Okay, so here's the equals to sign, so that's -1 plus 6 equals 5. Those all match. Yes, it's continuous. But we can't stop there. For it to be differentiable, it has to both be continuous and the limit of the derivative this should be as g of x differentiable at x equals -1, because that's the only point of interest. We can see that it's differentiable or continuous for the rest. So as x approaches -1 from the left, let's see what we've got. So first of all, g prime of x, I'm just going to take the derivative of each of these. That's 1 if x is less than or equal to -1. It's 2x, bring down the exponent, if x is greater than -1. So this is going to be the limit as x approaches -1 from the left of 1. There's nowhere to put in x, so the answer is just 1. Whereas the limit as x approaches -1 from the right of g prime of x, the function on the right is 2x. When we plug that in, 2 times -1 equals -2. Because 1 does not equal 2, the function is not differentiable. Okay, let's do our third problem, just asking after differentiability. Is h of x differentiable at x equals 1? That's our question. Okay, so first we're going to check on continuity. And when x is less than 1, the function on the left is -x squared plus 2. When we're approaching from the right, our function is -2x plus 3. And h of 1 is this one, -2 times 1 plus 3. So yes, it's continuous. So far, so good. Now we have to check with the derivative. So the derivative here is -2x if x is less than 1, -2 if x is greater than or equal to 1. And so let's check the limit as h prime of x as x approaches 1 from the left. So we can see that we're going to use the left one. Substitute in -2 times 1 equals -2. And then the limit as x approaches 1 from the right of h prime of x. It's going to be the limit as x approaches 1 from the right of -2. That's just -2. Notice how these two match. So that means that yes, h of x is differentiable right and left limit of h prime of x at x equals 1 are the same. Our final type of problem are mixed problems. An important thing to realize is just what knowing one of these pieces in terms of whether f of x has a limit, is differentiable, or is continuous, what does that tell us about the other ones? So let's start off. If f of x is differentiable at c, which of the following must be true? Okay, well, we know when we were doing the other problems that in order to tell if something was differentiable, we first had to know that it was continuous. So in order for it to be differentiable, it must also be continuous. Because if it's not continuous, it can't be differentiable. But it is differentiable, so it must be continuous. The limit as x approaches c of f of x exists. That means the left-hand limit and the right-hand limit are the same. That's part of our test for being continuous, so that must be true as well. If these aren't the same, if the left and the right-hand limit are not the same, then the function can't be continuous, then the function can't be differentiable. However, if f of x is continuous at c, which is true, f of x is differentiable at c, limit as x approaches c of f of x exists. Well, just because a function is continuous doesn't mean it has to be differentiable. If we went back to our little graph earlier, right here at this point, f of x is continuous. We don't have to lift our pen, but there's a sharp turn, so it's not differentiable. However, just like we said up here, this limit has to exist in order for the function to be continuous. If the function is continuous, then this limit must exist. So let's do that third one. If the limit as x approaches c of f of x exists, which is true? Actually, I should probably say which must be. Because it could be differentiable, it just doesn't have to be. F of x is continuous at c, f of x is differentiable. Well, looking back at that graph again, if we look here at this removable discontinuity, the limit from the left and the limit from the right are the same. The limit does exist, but the curve is not continuous, and so the curve is not differentiable either. So for this one, neither of these have to be. So it's basically a chain. If we know the limit doesn't exist, it's not continuous, it's not differentiable. If we know that it's continuous, then the limit must exist, but it doesn't have to be differentiable. If it's differentiable, then the other two have to be true as well, because they're prerequisites. Okay, let's look at two other types of problems. Which of the following must be true? Actually, this one can just be is, because we just have one function. F of x has a limit at x equals 2, f of x is continuous at x equals 2, and f of x is differentiable. At x equals 2. So let's start off with that limit. It has an overall limit if, I'm going to number these, let's do 1, 2, and then 3. So to find out this first one, limit, just overall limit just means that we've got the left limit and the right limit. So let's go ahead and find that. The left-hand equation is 3x squared. So that's 3 times 2 squared, or 12. And then the limit as x approaches 2 from the right. The right-hand function is x plus 10. So if we plug in 2, that's 2 plus 10 equals 12. So that means this one's yes. Is it continuous? That means, does this overall limit equal g of 2? Well, let's see. G of 2, it's equal to 2 right here, so that means we're using x plus 10, so 2 plus 10 equals 12. So yes, because this is the same as the limit that we found up here. And then finally, is f of x differentiable? So that means that the limit as x approaches 2 from the left of g prime of x equals the limit as x approaches 2 from the right of g prime of x. So g prime of x, if we take the derivative of 3x squared, that's 6x. Right there. If x is less than 2, the derivative here is going to be 1. Okay. The left function is 6x. Plug in the 2, that's 12. Limit as x approaches 2 from the right-hand function is 1. It's always 1. These ones don't match. So that means if we come back up here, differentiable, no, just the first two are true.